So here we are, and we're asked to implement this truth table using SystemVerilog. One thing to notice is that this is what's called a 2-bit decoder. And the reason it's called like that is because we have 2 bits in the input here. And we know that with 2 bits, you can have 4 possible combinations. And in the output, we have 4 bits. Well, actually, we have 3 bits in the input, if we count all 3 of these. But the leftmost is considered the enable, as I said here. And if we look at when enable is equal to 0, we see that we don't care about the other 2 bits because that'll produce a 0 here in the output. So let's look at these 2 bits again here. So we'll notice that they count from 0 all the way to 3. And then if we look at these 4 bits in the output, we see that we have unique combinations in each of these, in the sense that 1 bit is dedicated for 1 possible combination of the input. So this is something interesting and something we'll take advantage of when we design our circuit, or rather make our code. Okay, so I wrote over the some expressions for each of these codes. And if we look here, we have these P0, P1, P2, P3, and this is actually making reference to the individual bits here on the output. So if we look at the first one here, P0, we can say that P0 is equal to inverted version of A0 multiplied by the inverted version of A1. And this is how we can get this specific bit, right here. And then you continue this, so on and so forth, and then you'll end up with these 4 expressions that are very important to us. But then we're still missing the enable bit, and we have to take into account somehow. Okay, so here it is. I've written it out, and this time I called it output, right? Because this is my actual output with the enable bit taken into account. So what I'm doing here is, for each one of these bits in the output, I'm multiplying P0, P1, P2, P3 by the enable bit, right? So that means that for this decoder to work, the enable bit needs to be high. So additionally, obviously, this expression, you can implement it with an AND gate. So, that goes without saying. So now let's move on and let's see what this would look like if we were to create a circuit. So I've created this circuit here on the right, and you can see that if the way I implement this would be, wiring each and every of the logic gates according to the expressions that I found here. So, and let's look into this a little bit deeper here. So you'll see that I marked these bits here with P0, P1, P2, P3. So that simply means that P0 to P3 can be considered as internal variables, And finally, in the output, we have these set of AND gates here. And then that obviously comes from these set of equations. So this is how we get our output. So this is what the circuit looks like. But when we want to code this, we actually care more about our expressions here on the left. This is nice to have because it gives us a picture of what's going on. But what we need when we code it is really these expressions on the left. Okay, so I've started a new project here in ModelSim, and I've already created the folders that I need, the TB folder for test bench, the source folder, SRC, and the sim folder where the project is actually located. So let's go ahead and create a new file. So we want to go to source, select folder. I want SystemVerilog. I'm going to call this file DC stands for decoder to the 4. And then we press OK. Okay, and then right after, I also want to create my test bench file. So a new file. I'm going to go to Browse. I'm going to go to EB folder. Select that. I'm going to select Verilog for the language. I'm going to name this file decoder 2 to 4 underscore EB. Press OK. So now I want to go to my 2 to 4, DC 2 to 4, and then I want to go to edit. And then here we're now going to create our code here. So let's just begin a module DC by 4. In the end, we say end module. And now we want to declare our variables. There we go. So our input logic, this is our input variable. We're going to call it A. And then our output is 4 bits, so 3 to 0. We're going to call it out1. We close parentheses, and then we put the semicolon. So if you remember, our input logic is 3 bits. The third one is the enable. And then our output is 4 bits. So that makes sense with what we had earlier. Let's continue here. I'm going to say logic. You remember those interior variables that we were talking about? The P0s? Yeah, we're going to declare those now here. So now we can assign some values to these variables. I'm going to say, so it is at this point we go to our formulas here. And we see we want P0 to be inverted version of A0 times inverted of A1, and then P1 is A0 times inverted A1, and then P2, so on and so forth. And then right after that, I also want to assign my output variables. These are the final output variables of my module. So I'm going to go ahead and do that. Okay, so I've copied everything over here, and it's important to actually make a distinction for A2 here, because we know that A2 is the enable bit, and in the comment in this comment that I made here, I say that it is above all. It's sort of an exaggeration, sort of something kind of wild, but you know, it's true. If the enable is not on, then all of my output expressions are gonna equate to 0. So this is how we code it. Okay, so now we want to create our test bench file. So let's change files here. So I want to begin by declaring my timescale. So we want to work in the units of nanoseconds. And then our time step is going to be 10 picoseconds. And then we create our test bench module. So it's going to be decoder 2 by 4 underscore TB. And we pause that. We declare some logic variables. These variables are going to be my input and output. So my input is obviously 3 bits, right? I'm going to initialize it to 0. And then my output is going to be 4 bits. And I'm going to call it test out. And then we instantiate our circuit, or the 2 to 4 decoder. So I'm going to say 2 to 4 unit under test. And then here I'm going to relate A with the test input, and then I'm relating the output of the module with my test output. So now we can create our initial conditions. So I'm going to say initial begin. So our input, if you remember, 3-bit input, right? Because it goes from 2 to 0. So then I have to say 3 binary. So I'm manually setting each of these values here. And then we want a small delay here. So that's how you do it. Then what we do is we can copy this down actually. Okay, so I've created here all possible combinations, and so what we want to do now is we want to stop this test bench. And then finally we can end the initial begin module, and then we can just end the whole module. Well, I don't know if the initial begin is considered a module, but we have to end it here. So, and then we end the module. Then I want to go here, Control S for saving, Control S for saving, and then I want to compile all of this. So it compiled. So now what I want to do is I want to simulate. I go to Start Simulation. I go to Work. I want to start simulation on the test bench, because the test bench is what we need to do. We have an error loading design. Okay, it looks like we have the incorrect name for the module, so I'm going to delete that, save it, compile once again, simulate once again. It looks like I've created 2 modules, but this shouldn't be a problem. So I want to run this simulation for the test bench. Okay, so that works. So now I want to click on this, add wave, and then I want to change this to 100 milliseconds. It's not going to change much because we've already created a break in our test bench, but this will give us like enough space in case we need it. And then I run it. So then it ran the test bench, and then it got up to the line where it reached the stop. So then it stopped. I want to go back to the test bench. I want to do a full zoom here. So now we can move our cursor here. And actually we can look at this view. I think this view is interesting. And here it is. So then we have, when we have all zeros for the A2. Here, this is A2 here. We see that in the output we don't have anything. It's just zeros. And then it's only when we reach the enable key here and 1, we begin to see some numbers change here. And then you can see as we move along, we're counting upward, and then the bit is changing its location. So you can see that this 1 here is, it looks like it's like moving upward here on the graph. So this works nicely. So now the question becomes, how can I use this module to, create something more complex, something more involved. So we go back to our drawing here. What we essentially just created is this this box here. So now the question is, how do we use this to create, let's say I want to create a 3 to 8 decoder. Well, it turns out I can actually use this box that I made, and I would have to use 2 of them. So that's what we're going to do in the next video.